Okay. So the third experiment with the title of Determination of Potassium Permanganate Solution Absorption Maxima by using the UV vis spectro photometer. So in this particular experiment, you're supposed to start using or have hands-on experience on using the analytical instrument, and um, the instrument that you're supposed to be using is the UV visible spectrophotometer. Okay, it's actually a combination of two, which is UV spectrophotometer and also the visible spectrophotometer. As I think this one has been covered by Miss Yasmin in your lecture. Okay, there are two parts in which that the UV and visible, they differs by their wavelength range. Okay, normally the UV are between 200 and 400 nanometer, while the visible range is from 400 up to 800. So this is where your sample, okay, can be detected, okay, between this range. So the objective for this experiment is to determine the lambda max of potassium permanganate solution, um, and the basically the principle or the theory behind this is that you have this solution of potassium permanganate, and potassium permanganate, as you know, when you dissolve it in water, it will become a colored solution, and the color is very like dark purple or dark violet. Okay, and it is more suitable to be detected in the visible range. Okay, so the UV are mainly for colorless solution. So if you have any sample that looks like water, meaning colorless, don't have any color whatsoever, the range, the wavelength range that you are going to find the lambda max is normally between 200 up to 400 nanometer. But if your sample has colored, okay, colored solution, it produce colored solution, then most definitely the lambda max will be obtained between 400 to 800 nanometer. So what is lambda max actually? So lambda max is the wavelength at which your sample absorb the most, okay, absorb the light the most. That means when you plot a graph between absorption and the wavelength, the highest absorption, okay, that is the wavelength that will be considered as the lambda max. Later I'll show you some example of the what you call uh, spectrum. Okay, and then we look on the procedures. Okay, so there are two parts for this how to say experiment, in which that you have to prepare the sample first before you can start with any of the analysis. So sample preparation, okay, basically if your sample is already in liquid, then it might need some dilution, or it can be straight away what you call the analyze using the UV. But if your sample is in solid form, then it has to be diluted first, okay, into solution, and you can dilute it with any solvent that is suitable, meaning that if your sample needs to use organic solvent, then you can use organic solvent. Some sample, based on my experience, requires the use of acetic acid, okay, as the solvent. So as long as it can dissolve, your sample and turn it into a solution, then you can use it. Okay, unless you have a very advanced UV-vis spectrophotometer instrument in which it can straight away measure directly from solid sample. That means you don't have to uh, dilute it, okay, dilute or dissolve it into becoming a solution. Okay, there is UV-vis, okay, that can straight away measure the UV spectrum without dilution or dissolving it into solution form. So the sample that are going to be used in this experiment is the potassium permanganate. So you require potassium permanganate. So weigh accurately 100 milligram of this potassium permanganate, and it will be dissolved in 100 ml of distilled water. And this must be done in a volumetric flask. Okay, so in analytical chemistry or pharmaceutical analysis, a volumetric flask will be used when you want to prepare a solution. Okay, you don't use a beaker anymore, because in a volumetric flask there will be a graduated line in which that you know exactly what is the volume, and it has a specific volume. So once you have dissolved the 100 mg, okay, you weigh the 100 mg of potassium permanganate, place it into the volumetric flask, 100 ml volumetric flask, and then you have to top up it with some distilled water first. And for starters, you don't fill up until the mark, okay, there is a line at the neck of the volumetric flask. Okay, you don't fill up until that level. Normally we fill half or maybe 3/4 of the VF, and then you shake to make sure all of the solid has dissolved. So once everything has dissolved, then only you top up until it hit the graduation mark or the line to fulfill the 100 ml volume. Then the next step is you have to do a dilution. Okay, so the dilution in step number 3, you have to take 10 ml from the solution that you prepared in step 1 and 2, and you have to dilute in 100 ml. So again, you take 10 ml, and how of the solution that you prepared, you have to use a pipette. Okay, we don't use what do you call that, measuring cylinder anymore. Okay, we have to use a pipette, a 10 ml pipette. You suck this 10 ml of solution and place it into another 100 ml volumetric flask. Okay, then only you top up with water until it hit the 100 ml mark. Okay, then another dilution. So you have to do 2 times dilution. Now take 4 ml of the above solution, which is from step number 3, and again you have to use a pipette, a 4 ml pipette, suck the solution and place into a 10 ml volumetric flask. Okay, there is a 10 ml volumetric flask. Then only you top up with distilled water. So the final concentration that you obtain, okay, from the 2 dilution that you have done would be 40 microgram per ml. So this is the concentration of the potassium permanganate solution that you have prepared. So the next step would be the instrumentation itself. Okay, later we'll see some of the videos that I have placed on GC. Basically, the UV-vis instrument, the standard operating procedure will differ according to brand and also the type. But then again, the general method are always the same. Okay, it's like driving a car. Okay, there might be different brand, okay, different types, but then again, the purpose is to transport people, right? So just how you the step on what to do first, and in terms of switching on and all those things, okay, will be slightly different. Okay, in terms of UV spectrophotometer, there are two main types, okay, which is you have the single beam and also double beam spectrophotometer. Okay, the single beam only has one light source, okay, and the double beam will have two light source. And if we were in the lab, okay, the main difference to identify whether it is a single beam or not, when you open the sample compartment part, you will see that for single beam there is only one place to place or to put your sample or sample holder. There will be one slot for sample holder, but for double beam, okay, there will be two sample holder, two different sample holder to put in your uh, cuvette. Okay, and then what we normally do, okay, like general rules for using the UV spectrophotometer, you have to switch on, and then it will do the self calibration. Okay, the instrument will self calibrate, and this will take about 10 to 15 minutes. Okay, so what we normally do is before you start preparing your sample, you switch on the UV spectrophotometer first, so that it has time to stabilize. Okay, that is one thing about using analytical instrument. Okay, you have to switch it on earlier so that it has time to stabilize itself. Okay, same goes later. The next few experiment, like using the IR or the HPLC GC, so that requires longer stabilization time. Okay, like for example the HPLC, okay, you need it is best to let the instrument stabilize for up to half an hour. Okay, back when I was working in the lab, normally I will just let the instrument stabilize for up to 1 hour before I introduce any sample or run any sample to analyze. Then the once the instrument has stabilized, okay, step number 6 says set the absorbance at 0 by using distilled water as blank. Okay, um, blank measurement has to be done. Okay, even when you are doing titration, okay, you have to do a little bit of blank. Same goes for UV, IR. Okay, you have to measure the blank. So the blank in terms of UV spectrophotometer would be any solvent that you use for the dilution process or the dissolving process. Okay, like in this particular experiment, you dissolve your potassium permanganate with distilled water. Okay, just distilled water. So that would be your blank. But in the case that, let's say, you use ethanol or maybe methanol as your solvent, so those alcohol will be treated as blank. Okay, you need to measure the blank so that it will eliminate the reading for that alcohol, so that later on when it measure the spectrum, all of the reading will be basically or solely the sample itself. Okay, it means the instrument will do it for you by deducting the reading of the solvent that you are using. So then take the adsorbent of the resulting solution at different wavelength, plot the graph between wavelength versus observed adsorbent, and write your report. So over here, okay, there are wavelength from 400 up to 750 nanometer. So that means at each of these wavelength, you are actually supposed to measure the absorbance just by putting the sample into the instrument and press start. There will be a display on the instrument in which that you can read the value of the absorbance. Okay, so basically once you have this, you need to plot a graph between absorbent versus wavelength. Absorbent will be on the y-axis, wavelength on the x-axis. So from here you will find out, okay, which will be the lambda max. So lambda max is basically the peak, okay, the peak, the highest absorbent. So, and trace it down to find out at which wavelength. So that would be your what do you call that, lambda max. So that is basically the lab manual. I know there is no pictures or anything, but it's okay. We'll look into the uh, videos first. Okay, but before I show you the videos of the instrument, I want you to watch this sort of the theory behind spectrophotometer, which is the Beer-Lambert's law. Okay, so this is the formula or the theory behind the UVV spectrophotometer. So watch this first.
Let's talk spectrophotometry. He knows a lot about the science stuff. How quickly we have learned in a previous tutorial. Kinetics is the study of reaction rates. Sometimes we will want to know how quickly or slowly a chemical reaction will happen. Therefore, any kinetic study will require monitoring the concentrations of a particular reactant or product over time to see how quickly they are being used up or formed. Of course, we can't see molecules and count them. They are just too small and too many. So to do this, we have to be clever. We can measure the mass of a precipitate as it is forming, or we can measure the volume or even the pressure of a gas that is produced over time. But what if a reaction does not produce a product in a different phase than the solution? Luckily, one of the most reliable methods involves using spectroscopy, which is the study of how light interacts with matter. So let's learn about this technique now. All molecules absorb and emit light differently based on what kinds of covalent bonds are in the molecule. If the products and reactants interact with light differently enough that there is a color change as the reaction occurs, we can monitor this process with an instrument called a spectrophotometer in order to measure changing concentrations. This will give us data in the form of an absorption spectrum, which displays how much light through a band of frequencies is able to pass through a sample to reach the detector. Where there are peaks, it means that not as much of the light of that wavelength is getting to the detector, which means that it is being absorbed by the sample. If we collect data like this continuously over the duration of a chemical reaction, we can gather information about how rapidly the absorbance changes, and thus how the concentration of a particular substance is changing over time. In order to do this, we will use an equation that relates the amount of material in a sample to the absorption of light passing through it, and this is called Beer's law. Here, A is for absorbance. This symbol represents something called molar absorptivity, a measure of how well a chemical species absorbs a given wavelength of light. B represents the path length, or the distance light has to travel through the sample, which is relevant because the more of a substance the light travels through, the more of it that will be absorbed. And C is the concentration of the sample, which again is relevant because the more concentrated, the more absorbance that will occur. Absorbance is measured by comparing the intensity of the beam of and the intensity as it leaves the sample and strikes the detector, which are I0 and I respectively. And A will be equal to the log of I0 over I, or equivalently, the negative log of I. If we plug the latter version into the original equation, substituting for A, and then solve for I, we can get this version of the law, which displays the exponential relationship between variables that are easily measurable. The primary advantage of this technique is that we can just let a reaction occur normally and measure the rate indirectly by analyzing the light that interacts with the components in solution, rather than stopping the reaction and measuring concentrations directly. Let's try one calculation. Has a molar absorptivity of 0.35 inverse centimeters inverse molarity. Light passes through a 2 centimeter sample and hits the detector with an intensity of 0.12 compared with the incident beam. What is the concentration of the sample? If we want to use the more basic version of Beer's law, then first we need to calculate the absorption. We can use this simple equation from before, plugging in 1 for the initial intensity and 0.12 for the other intensity. That gives us 0.9208 for A. Then we will use Beer's law. We can rearrange to solve for C, our unknown, plug in the absorption we calculated, plus the 2 given values, and we should get around 1.3 molar for the concentration of the analyte. Gathering this kind of information regarding concentration and plotting it in real time using computer software will allow us to easily infer all kinds of things about the rate law and hence the reaction mechanism for the reaction that is happening in solution, which is incredibly useful data. To get just a bit more practice, let's check comprehension.
Okay, so that is the theory behind the UV vis spectro photometer, okay, which is the Beer-Lambert's law. And then I'm going to show you the instrument, or wait, yeah, this one.
Here we have a spectrometer, and today we are going to show you how to use it. The spectrometer is known more commonly as the Spec 20, and its production began in 1953. First, this is the sample holder. This is where you will insert the cuvette with the liquid you want to measure. This is the display, where the values will be shown. This is the wavelength knob. It adjusts the wavelength of the light that will send through the solution. Lastly, this is the calibration button, which is used with lighting machines to ensure the accuracy of the measurements. These machines used in schools can cost up to $10,000, so be careful. The cuvettes are relatively inexpensive, but still be careful because rubber glass is dangerous. You will also need Kim wipes when using the Spec 20 to clean off the cuvettes. Any fingerprints could change the results. Kim wipes are around $15. To blank the Spec 20, fill the cuvette about 3/4 full of water and place it in the sample holder. Then, use the calibration button to set the absorbance to 0. You will need to do this for every solution. Now the machine is set to test your solution. Make sure the wavelength knob is set to the appropriate wavelength for your experiment. Place the cuvette with your solution in the sample holder. Then, watch the display for your measurements. The lower the absorbance, the more light was reflected. Interesting fact! The Spec 20 is now produced in Madison, Wisconsin. Spec 20s are useful for measuring reactions that result in changes in color and can also be used for hematology to measure the concentration of red blood cells. Have a good time. We hope you learn a lot.
Okay, so now we will rewatch again, and I will try to further explain some of the function of each of these instrument.
Here we have a spectrometer, and today we are going to show you how to use it. The spectrometer is known more commonly as
So this version of spectrophotometer, I would say this is a single beam. Okay, because how I know? Because the slot where you can put the sample or the cuvette holder is just one, meaning that when you want to put the blank and also the sample, you have to switch, okay, between those two cuvette. Unlike for double beam, there will be two slot, so you can just place the blank one and the sample in another slot. You don't have to like take it out every time. Just just changing the wave. Okay.
Spec 20, and its production began in 1953. First, this is the sample folder. This is where you'll insert the cuvette with the liquid you want to be measured.
So that will be the place where you insert the cuvette. Okay, and the cuvette, uh, the material, okay, of the cuvette, the most common and cheap one is made out of plastic. Okay, but being a plastic, sometimes if you place colored solution, the color, if you don't clean it properly, the color might stick, and sometimes you're gonna have residue on the plastic of the plastic cuvette. But then again, because it is cheap, so it can be replaced at shorter interval of time. Okay, other material that can be used includes glass. Okay, like in these videos, she used glass. But one of the best material that you can use for the cuvette or the sample holder is quartz. Okay, quartz crystal. Okay, like the quartz in the use in the watch, okay, on your wristwatch. So the quartz has a very inert property in which that it doesn't interfere with the reading. Okay, it doesn't like absorb any light, uh, thus giving false reading for the sample.
This is the display where the values will be shown.
So on our UVV spectrophotometer in the lab, okay, in campus, okay, there will be a display like this as well, in which you can see what is the absorbance reading. Okay, and most of these UVV spectrophotometer can be connected to a PC. Okay, given that there is a software installed on the PC that can control the instrument itself. Okay, but most has uh, these abilities whereby you can digitalize it, in which that you can connect to a PC or directly to a printer, so that you can print out the result.
This is the wavelength knob. It adjusts the wavelength of the light that will send through the solution.
So this is how you change the wavelength. Okay, like earlier, if you notice on the lab manual, whereby you have to measure the absorbance at different wavelength. Okay, like from 400, 410, 420, 450. So this is how you change the wavelength in this instrument. In the video, you have to you use a knob lah, in which you twist clockwise or counterclockwise. But in our lab, it's just a button. Okay, you can press up or down. So this is the wavelength. Okay, you can just press up, or you want to decrease, press down. The other UV-based instrument in our lab, you can straight away input number. Okay, let's say you press 00, or you want to change to 700, you can straight away put 700. Okay, no need to twist the knob or just press a button. You can straight away input the wavelength that you want.
Lastly, this is the calibration button, which is used when blanking the machines to ensure the accuracy of the measurement. These machines used in schools can cost up to $10,000.
So this version already costs like 10,000. To me, this is quite cheap, in which that it is very simple. The one in our lab, the double beam, okay, single beam will definitely cost cheaper. The double beam version, most of the time it is double the price. If I'm not mistaken, the one in our lab costs like 70,000 plus, close to 80,000 ringgit. Okay.
Be careful. The cuvettes are relatively inexpensive, but still be careful because broken glass is dangerous. You will also need Kim wipes when using the set 20.
So before you place the sample or the cuvette into the sample holder, you have to wipe out the cuvette itself so that there is no dirt, and also what you call that, there is no fingerprint, because you don't want any of that to interfere with the reading. And we normally use tissue, okay, tissue paper, or even in these videos she used Kim wipes. So Kim wipes is like the expensive version of tissues, mainly used to wipe all of these tiny dirt particles. Okay, and this is quite the Kim wipe is expensive, but in our lab normally we just use the tissue paper.
Could change the results. Kim wipes are around $15. To blank the spec 20, fill the cuvette about 3/4 full of water and place it in the sample holder. Then,
So before you can measure your sample, okay, as in the procedure, you have to measure the blank. So the purpose of putting the blank is so that you can on the instrument we call it as auto zero, or doing a baseline correction, in which that the reading will not include the solution or the solvent that you are using, so that when you place the sample, all of the absorbent that will appear, the results is just based solely on the sample itself, okay, without the addition of your solvent.
use the calibration button to set the absorbance to 0. You will need to do this before every new solution. Now the machine is set to test your solution.
So every time you change the wavelength, okay, the wavelength, and also the different blank is used, you have to do that baseline correction or the auto zero reading. That means if you are using the same blank, that means each time you change the wavelength, let's say from 400 to 450 to 500, you have to do the blank correction. Okay, but if you are still using the same wavelength, okay, and also same solvent as blank, then you don't need to what you call that, do the blank correction. Straight away you can measure all of the sample. Okay, so that has to be done every time you change the wavelength, or if you use different solvent as blank.
Make sure the wavelength knob is set to the appropriate wavelength for your experiment. Place the cuvette with your solution in the sample holder. Then, watch the display for your measurements. The lower the absorbance, the more light was reflected. Interesting fact! The Spec 20 is now produced in Madison, Wisconsin.
Okay, this video is finished. Now, this one. Okay, you watch this first, and then we'll rewatch again, and I will comment. So this is the same UVV spectrophotometer model as what we have in our lab. Okay, so we rewatch again, and I will add some explanation. So the brand of UV that is available in our Shimatsu, and we actually have both the single beam and double beam. But in this video is the double beam version, the Shimatsu UV 1800. So these two glass thing that you are watching right now is what we call as a cuvette. And in the earlier video, their cuvette is slightly different. It looks like a small test tube. But the most common shape of cuvette is this like square cylinder. Okay, it's not a cylinder, it's round, but this is square cylinder in which that there are four sides. Okay, and two of those sides is transparent, and the other two sides will be translucent or sort of like opaque. Okay, the transparent side will be where the light will go in and also go out. Okay, and this is and I think the one in these videos, the cuvette is made out of quartz crystal. Okay, so let's see. So here he said that pipette or place the appropriate solvent, the same as those used to dissolve the analyte. That means the solvent that you are using to dissolve your solid sample. So only handle the opaque side or the translucent side, meaning that when you want to hold the cuvette, okay, you hold on the opaque side, not on the transparent. Okay, because on the transparent side is where the light will come in and also go out. So we don't want to have any dirt or any what you call fingerprint. Okay, as it will affect the reading of the absorbent. So make sure there are no air bubbles as well when you are placing the blank. Okay, so this is the shape of the UVV spectrophotometer. Okay, exactly the same. And there are two. What he's doing is he opens the sample compartment part, and as you can see, there are two holder in which you can place the cuvette. And this version is a double beam UVV spectrophotometer, so you can place two cuvettes at the same time. Okay, you don't need to like put in and then take out and then put in another cuvette. So you can place two cuvettes at the same time. And what he's going to do right now is to do the blank correction reading. And for the blank correction using the double beam, you have to place both cuvette with the blank solution or the solvent. Okay, unlike single beam, there is only one slot, so you just need one cuvette with the blank solution to do the blank correction reading. But for double beam, both side of the sample slot over here has to be inserted with cuvette containing the blank solvent. And also said, wipe the optical faces of the cuvette, then only place them into the instrument. And then when you want to place the cuvette into the instrument, okay, unlike the previous video, the cuvette all are transparent. So there is no, how to say, worried in which that the light won't pass through or won't pass through your sample. But in this type of cuvette and also instrument, okay, you have to make sure that the transparent side has to be placed correctly in order that it must be in the light pathway. Okay, so based on these videos, okay, the light will normally pass and this particular instrument, it will pass from the right hand side to the left. Okay, so the right hand side to the left. So you have to place the cuvette properly in order so the light can pass through. So wipe and then place. So he is only wiping the transparent side. Okay, so that is the transparent side. And watch how he hold the cuvette. Okay, now this is where it's slightly different. Okay, his instrument is connected to a PC, a computer, so he can control using a software. But in our lab, it's all has to be done on the instrument itself. Okay, as you can see here, wait, okay, there are buttons. So just by using this button, you can set up same thing, how to do the blank correction reading and how to do the sample reading. All can be done over here, and the display will be right above, which is slightly small screen, but everything will be shown here, and it can still function as if you are using the what do you call that, software. Okay, but using the software is much more easier lah than pressing, because you are just using the mouse. So now what he is doing is the blank correction reading, or sometimes also known as baseline correction. And this can be done, and for this version, unlike the previous video, you have to twist the knob. The measurement has to be done at one particular wavelength at a time. But using this double beam spectrophotometer or slightly advanced version, which is like this one, you can actually straight away do a range. A range means from, let's say, 400 to 800. Okay, or from, maybe you want to start from 300 to 700 instead of doing one by one. or doing 300 first, and then 310, 320, 330, and so on until you reach 700. So that will take slightly a longer time. But using this method, okay, you can set a range of wavelength that you want to measure. Okay, so he is doing the setting the range of wavelength and pressing the baseline for the baseline correction or the blank correction. So now, once that is done, okay, you can now start to measure your sample. Okay, but when you want to measure the sample, you don't need to take out both cuvette. Okay, just take out the front cuvette because that will be the place where you put your sample. The one at the back will remain as blank. Okay, it needs to be placed there, or what we call as the reference. So take out the front cuvette and place your sample in it, and you can put it back. So that is the sample. Put it into the instrument, and you can start doing your measurement. If in our lab, okay, basically, basically once you place the sample, there is this green button on the corner, the right hand side at the bottom. So there's green button, start stop. Basically you just press the start button and the measurement will be done by instrument, and the absorbent will appear on this tiny screen. So you just take that absorbent reading. It is as simple as that. But this guy is using the computer software, so it can straight away plot a graph for you. The one in our lab manual, you have to plot the graph manually. You take out the absorbent and then determine where is the lambda max. But from here, okay, this example, the lambda max actually can be detected using the software, but as you can see, you have to find the peak. So the peak will be around, if you can see my arrow over here, so that will be the peak. Okay, and trace it down to the wavelength. So that is how you find the lambda max for any sample. Okay, but if using software, what he will do next is select the peak. Okay, so now he use the option of peak to select the lambda max. So that is exactly the same UV spectrophotometer as what we have in our lab. Okay, let's see this one. Last videos. The other two you can watch later. So preparing the stock solution is, if we want to compare with our lab manual, is step 1 and step 2. Okay, you prepare that first solution before you dilute. So that is called as a stock solution. Okay, when you want to top up the distilled water, okay, into the volumetric flask, when it is almost reaching the mark over here, okay, always use a dropper, because if let's say you overshoot and what do you call that, add in too much water until it is over the supposed mark, that means the concentration already is different. So you have to redo it again, I mean weigh and prepare again. So shake to make sure all solution is homogeneous. Okay, so that is your stock solution, or from step 1 and step 2. So this person is actually preparing the what do you call that, standard curve. So that's why he prepared 4 different concentration. Okay, so this is exactly the same as in our lab manual. So he start at 400, then 420, 440, up to 600 nanometer in order to determine the lambda max. Okay, so at every wavelength, different wavelength, so you take the reading of the absorbance in order to measure the, or sorry, to plot a graph so that you can extrapolate the lambda max. Okay, this one is calibration curve. Okay, it's not included in our current experiment. But then again, this is done if you want to detect the unknown concentration, okay, for potassium permanganate. But you can only do this after you have the lambda max, because you need to measure the all of the potassium permanganate at the wavelength of this lambda max. Okay, so I'm just going to show you all those 4 videos first. Okay, and there are 2 extra videos in which you can watch later. These 2 are slightly longer. Okay, but they are still the same, which is spectrophotometry analysis of potassium permanganate as well. Okay, using maybe slightly different brands of the instrument UVV spectrophotometer. Okay, you may see from the 3 videos earlier or 4 videos the 3 types of UVV spectrophotometer, but the basic concept behind the measurement or the analysis is still the same. Okay, even though all are different brand, but they give you the absorbent reading in which you can find out the lambda max. Okay, so for this experiment, sadly there is no screen experiment. Okay, like the titration, I cannot find any screen experiment for the UVVs, but then again, for the result, okay, how are you going to do the report? So basically the procedure, everything is almost the same, but the report itself, okay, let's go back to the manual. Wait. Okay, here basically what you have to do is find out the absorbance, but how are you going to measure the absorbance with no sample and no instrument? But no worries, okay, this what I want you to do is find these values from any literature online. Okay, don't worry, because there are a lot of sample uh, reports, okay, lab reports, and also in article journals that gave you the absorbance for each of these wavelength. And uh, it doesn't have to be the same concentration as this. Okay, no need to bother about what is the concentration of the potassium permanganate solution. Just take whatever values for the absorbent. Okay, so all of this can be obtained online, okay, in which that you can find a report or an article basically on the lambda max for potassium permanganate. Okay, I have tried to search for it, and there are many examples. So definitely, I think there will be no trouble for you all to find all of this. So once you have the absorbance, so plot a graph in which so that you can identify which of these wavelength is the lambda max. Okay, so you have to identify. So let's say the lambda max of potassium permanganate was found to be at, let's say, 600 nanometer at absorbance of something something, maybe 0.25, for example. Okay, so find the absorbance from online literature. So that would be all for experiment number 3, which is the determination of potassium permanganate lambda max. So any questions?